So today we're going to go through a quick example of using superposition and our beam tables, beam deflection tables if you will, to calculate the reactions for a statically indeterminate beam using the method of superposition. And from there we'll just go ahead and do the shear force bending moment diagrams and some extra wee calculations. So the problem as laid out, so we have a propped cantilever, so coming out of a fixed support at A and propped at the other end at C. We have a uniformly distributed load on the far end from B to C for the outside 2 meters of 5 kilonewtons per meter. And we have an E and an I given there because we asked to actually calculate deflections later on, so we're going to need that. But for the most part, the main part of the question is to find the reactions at the supports and draw the free body, shear force, bending moment, and displacement diagrams. And as I said earlier, we're going to do that using superposition, our beam deflection tables, and so that's what we're going to do. So let's get into it. So the first thing I need to do is to break my system into a primary system and a redundant system. So we know it's statically indeterminate to the first degree because we have one extra reaction that we don't have an equation to resolve for using statics. I'm ignoring my x direction because that just goes to 0, so that's somewhat trite. So we have the free body diagram already done up. We have the 3 reactions, the moment at A, reaction at AY, and the reaction at CY, but we only have the 2 equations. Sum of the moments about any point equals 0, and the sum of the forces in the Y direction equal to 0. So we're going to have to come up with one compatibility equation to augment our equations of statics in order to resolve the system. So the first step then is to draw a primary system. So I'm just going to label these. So we're going to have a primary system and we're going to have a redundant system. Now, in choosing the redundancy, of course, what I want to do is I want to leave myself with a primary system that is fairly easy to look up in the beam tables and stuff like that. So in this case, probably the simplest one to do is to leave ourselves with a straight cantilever and to make the reaction at C the redundancy. And so that's what I'm going to do. So I'm going to go ahead and draw my primary system. So I'm going to put in my 2 reactions at A. So we have moment at A, and I'm going to give it a prime because it's only part of the primary system, not the actual moment at A. And same thing for reaction AY prime. And we have our uniformly distributed load. So I'll put it in here. And I can go ahead and approximate our deflected shape. So it'll come out with a slope of 0 from the support and slowly bend down to there. So now what I need to do using superposition, basically what it says is that free body diagram or the final system, original system, has to be equal to the sum of our primary system and our redundant system. So what I need to do now is go down here and I will add our reactions again. So that's moment at A, in this case a double prime, our reaction at AY double prime. And we've already got the uniformly distributed load in the primary system, so we don't need to add it to our secondary system again, but we do need to accommodate the reaction at CY. So in this case, I'm actually going to choose to draw it in as if it was an applied load. That's the way we're going to treat it. Even though it is a reaction, I'm going to treat it in this case as if it was an applied load. Now, I don't need to put a prime or a double prime because there is only the one RCY. So RCY of the redundant system plus nothing added in the primary system equals RCY in the original system. So we're good there. And again, I'm going to approximate my deflected shape. It's still a cantilever, so it's going to come out with a 0 slope at A. And in this case, it's going to bend up slowly at the end. And I'd like to mark my deflections because that's where we're going to get our compatibility equation. I'm going to mark my deflection in here, and that's going to be the displacement at C prime, and the deflection down here is the displacement at C double prime. One other thing I want to do is note on the original system that, of course, the displacement at C has to be equal to 0 because there's a support there. And so that is going to give us the logic of our compatibility equation. So let's just label that compatibility equation. And using the logic of our system, that basically says that the displacement at C, displacement at C is equal to the displacement at C prime plus the displacement at C double prime. Keep in mind you have to get your sign conventions the same, and that has to be equal to 0. So we're just going to go to our beam tables, and I've popped in or pasted in a couple different situations, one for the load at the extreme end of a cantilever, the other for a UDL on the partial UDL on the cantilever, and the respective equations that they give for the maximum displacement at the end, as well as the displacement at some position X along the beams. And so that's what we're going to use to engage our compatibility equation and solve for one of our reactions. So I'm just going to identify then from the beam tables, we know that the displacement at C prime is a resultant of the partial uniformly distributed load. So that means we're going to be using this equation in here. And so W over 24 EI all multiplied by 3L to the 4th minus 4A to the 3rd L plus A to the 4th, and delta double prime C is equal to, I'm going to drop the negative sign for now, PL over 3EI. Okay, so by dropping the negative sign in both instances, making them positive values, so that's going to give me a positive displacement down if I put my loads in as positive down. So I'm going to keep that sign convention. If the force is actually going upwards, then I will introduce a negative sign for the force, which will reverse the displacement. So that way I can make sure that I have compatibility in signs. So now let's go ahead and do our compatibility equation. So displacement at C is equal to 0, which is equal to delta C prime plus delta C double prime, which is equal to, and I'm going to substitute in our values here. So that's 5 kilonewtons per meter divided by 24 EI. I'm not going to bother to substitute in for EI because they'll cancel out in this instance. And that's 3 times 5 meters all to the 4th minus 4 times 3 meters cubed times 5 meters plus 3 meters all to the 4th. And so that's the partial uniformly distributed load. Now delta C double prime, so that's from the point load. And so that's going to be equal to negative RCY. So I'm just giving it a negative sign to indicate that it's going up. and our 5 meters all cubed, all divided by 3 EI. And if you look in this, you will see that the only unknown is RCY. And we're able to solve for RCY. Say RCY is equal to 7.08 kilonewtons. And I'm just going to highlight that as one of our answers. So now, having used our compatibility equation, effectively solved for one of our reactions, we're now down to a problem in statics because we still have 2 equations of statics which we can apply. We're down to 2 unknowns, so it simply becomes a matter of applying our static equations in order to resolve for the other 2 reactions. So let's label that. We're going to use our equations of statics. We're going to start with the sum of the forces in the y direction is equal to 0, which is equal to RAY. And we're applying this to our original system. We're finished now with our primary and redundant systems. And that's 5 kilonewtons per meter multiplied by the 2 meters over which it applies, plus our RCY, which we know is a value of 7.08 kilonewtons, and allows us to come up with RAY is equal to 2.92 kilonewtons. Go right on to our next sum of the moments about A, and I'll use this as positive. Set it equal to 0, and we have our moment at A plus our UDL again, which is 5 kilonewtons per meter over the 2 meters which it is applied, and the moment arm to its centroid then is 4 meters minus the reaction at CY, which still is equal to 7.08 kilonewtons multiplied by its moment arm, which is 5 meters. And that allows us to calculate that the moment at A is equal to 4.6 kilonewton meters. So that's the main part of the question. To be fair, we do want to do the shear force bending moment diagrams. We're going to use the graphical method. If you're not familiar with the graphical method, I will put a link to another more fulsome description of the graphical method for shear force bending moment diagrams. But in the meantime, I'm just going to very quickly go over and employ it. So to do that, first thing I want to do is to label what these are, because it'll make my life easier. So that's equal to 2.92. That's equal to 7.08. And the moment is 4.6. Okay, so the shear force diagram then up to 2.92. We'll get that started. 2.92. 2.92 stays uniform across where there's no other loads being applied, at which point it starts to go down from constant. We're going to go to linear. It's on a negative slope, and if we look at the area under that curve, it's going to drop down and arrive at a value of negative 7.08, and then the reaction pushes that back up to 0. Okay, and the step to get from a shear force to bending moment diagram, it'd be helpful to just note a few things in here. So I'm going to note some of the areas. So the area here in that is equal to 8.76. area in here, 0.8526, and I'm just using similar triangles to figure out what that distance is in here. That distance is 0.584, in case you're wondering, which allows us to calculate the area in here is 5.013. And so when I do the bending moment diagram, of course we have that point moment at A, which is going to push us down for an initial start, and we're going to come down, where is it? That value is negative 4.6, and then we have constant shear force diagrams, so we're going to go up at a linear, and if I add to the negative 4.6 the area under a shear force diagram, that will take us up to a value of 4.16. I see I have my proportions off a little bit here. And that's going to continue up and sloping down and get to a zero slope at that nexus point there. And that value is 5.013. And then if we subtract the area of 5.013, that allows us to slope back down and come back to our endpoint here. And if I were to draw in our deflected shape, we have it's coming out and then it bends back up to our support. So that pretty much resolves the system. Now all we got to do is go back to the question, make sure that we've answered everything, and the additional question that it asks is to calculate the deflection at x equals 2.5 meters from A. So we're going to apply those other two equations using our systems to figure that out, again using superposition. So what I'm going to do is I'm going to mark our displacements at x equals 2.5 meters, so that's somewhere around here, and that'll be the displacement at 2.5 prime, and here displacement at 2.5 double prime. And so now I can go about getting our deflections at x equals 2.5 meters. So our deflection at 2.5 is equal to our deflection at 2.5 prime plus our deflection at 2.5 double prime, and deflection at 2.5 prime is equal to W bx squared all over 12EI times 3L minus 3A minus 2x. And substituting in our values, then we have 5 kilonewtons per meter times 2 meters times 2.5 meters in our position x all squared, and that's equal to 12EI. Okay, we need to put in our values for EI. In this case, we want to make sure we have compatible units, so we're going to have to take our 200,000 and multiply it by 10 to the third, in order for it to be in kilonewtons per meter squared. And our I is already in meters to the fourth, so 4.91 times 10 to the minus 6 meters to the fourth. And we multiply that by 3 times our length, which is 5 meters. Minus 3 times A, which is 3 meters. Minus 2 times x, which is 2.5 meters. And so we calculate that out and we come up with 0.1008 meters. And then we need to go back and calculate delta 2.5 double prime, and that's equal to negative RCY multiplied by x squared all over 6 EI, which is equal to, oh, sorry, I missed a part there, x squared multiplied by 3L minus x. So substituting in our values, we have RCY 7.08 kilonewtons times 2.5 meters squared all over 6 EI, so 200,000 times 10 to the third kilonewtons per meter squared times 4.91 times 10 to the minus 6 meters to the fourth. Extend that out. And that's times 3 times L, which is 5 meters, minus X, which is 2.5 meters. And we run those numbers and we get negative 0.0939. And as we said before, delta 2.5 is equal to delta prime 2.5 plus delta double prime 2.5, and that is equal to 0.0069 meters, or about 7 millimeters. And we can show that in here, so that distance in here to be about 7 millimeters. And there you go. So that's how we can use the beam tables and superposition to resolve a statically indeterminate beam to derive deflections or its reactions along the beam. Hope you found that useful.